To find the irregular area beneath this curve, we treat the right boundary as a movable point, x. As x slides, the region expands and contracts. This creates an area function, a of x, outputting the total size based on the boundary. This perspective shifts the focus from the static shape itself to how that shape grows, the necessary starting point for linking area to the derivative. Think about nudging our boundary forward by a microscopic step, dx. This adds a tiny vertical sliver of area to our total, with a height determined by the curve at that point, f of x. Since this step is infinitesimally narrow, we can treat this sliver as a simple rectangle. The area of this sliver, dA, is the product of its height and its width, f of x times dx. If we look at the ratio of this added area to the width of the step, we find that dA over dx equals the height of the curve, f of x. In calculus, a change in output over a change in input is the derivative. This shows us that the derivative of the area function is the original curve itself. This realization changes the nature of our problem. If we want to find a function that describes the area, we are now looking for a specific function whose derivative is the height of the curve. Let's test this with a specific curve. The function f of x equals 8x minus x squared. To find our area function, we have to work backwards. We need to find a function that, when differentiated, results in 8x minus x squared, a process known as finding the antiderivative. Using the reverse power rule, try it yourself. Pause the video now to see if you can find the antiderivative. This new equation tracks the accumulation of area at every point. It represents the sum of those infinite slices without requiring you to calculate each rectangle individually. We represent total area using definite integral notation. To find the space between starting bound A and ending bound B, we evaluate the antiderivative at both points. You evaluate the top bound and subtracts its value at the bottom bound. By focusing on just these 2 points, you bypass the need to manually sum the infinite number of slivers between them. This relationship, using the antiderivative to solve for cumulative area, is the fundamental theorem of calculus. It proves that integration and differentiation are inverse operations. One measures how a total accumulates, and the other measures the rate at which that total changes, allowing each to perfectly undo the other.